Hello, this is my model of a high-performance liquid chromatography system. It is not 100% spatially accurate and not really to scale. So we're going to start off with our solvent system. A unique thing about the HPLC is that it uses a multi-solvent system in order to control the amount of compound components that are going through the column at a given time. You can change the relative polarity of the mobile phase by changing the ratio of these solvents to each other. So if you have a nonpolar compound stuck in the column, you can change the polarity of the system to be more nonpolar by impacting the solvent system and make that compound elute faster. The one caveat is that the solvents must be miscible with one another so that no globules form to clog the column. Now we move over to the pump. We're dealing with a very dense stationary phase in our column, so we need pressure to push the solvent and the sample through the stationary phase faster. At TU and most other places, you typically use 300 to 400 bar from a pump. Now we move on to our injector. And we have an auto sampler port, similar to a GC. So an interesting thing about the samples is because they stay in the liquid phase throughout the entire system, we're able to analyze larger and more complex molecules than we would with the GC, because the GC heats their samples in order to get them to a gas phase, and that's not great for the larger, more complex molecules that are typically more unstable at higher temperatures. Another interesting thing is that we have these things called vial inserts that can be used on samples on a microliter scale, so you don't have to dilute your samples to a larger volume. The vial samples make it so that the auto sampler can suck up a much smaller amount than typical. Now we're moving on to our guard column and the HPLC column. And we're using a column that is about 5 to 25 centimeters long, and it's made of stainless steel in order to withstand the pressure coming from the pump. And we also have this short guard column that will protect the actual column from contaminants. Now, our stationary phase that is most common for HPLC is a packed column. And this column is packed with beads that have various compounds attached to them based on the type of the polarity of the phase that you're looking for. Now, the most common is carbon 18, which is nonpolar, and that's for the stationary phase, which means that the beads have 18 carbon chains attached to them. Now, if you want to change your polarity, you can use a column with beads which have different compounds on them to best suit the analyte you're looking to analyze. And that means that you can either change the length of the carbon chain or have completely new substituents. This is where we branch off to having two separate options. The first option is to have an HPLC that solely uses a UV-Vis detector, and the second option is to have one that uses an tandem MS system as well as a UV-Vis or just an MS system. So looking at the first one, as the molecules go through the UV-Vis, they're absorbing at different wavelengths in the UV-Vis spectrum, and this detector can analyze those molecules passing through selectively and non-selectively. What you do is you choose a wavelength you believe to be relevant for your UV-Vis detector to emit, and the detector will make note of the compounds passing through that absorb at that light after the compounds have been separated. Now, you do need to make sure that the analytes and solvents have the absorb at the same wavelength in the region that you've chosen. So an advantage is that we can target specific analytes and see exactly when they come off. But a disadvantage is, as previously mentioned, you need to make sure your analyte and solvent have the same wavelength, because if they're different, then you can end up with peaks that seem to be the same or hidden behind each other, or you'll only see the peak of the solvent or only see the peak of the analyte. They need to be two distinct peaks that absorb at the same wavelength in order for a clear reading. And as the compounds pass through, of course, there's typically a waste system for fractions or just pure waste to go. And it will also send the information over to a computer program to be analyzed and tell you which compounds are absorbing at what peaks. Now, for the second option, we're dealing with an MS. So you put the MS after the HPLC because you want the HPLC to separate the components first and then let the MS tell you the molecular weights of the components at certain times so you know how they've separated. Now at TU we use a tandem MS system, which means we have two MS devices hooked up together in a series. Now the first one acts as a mass filter to give an initial reading of the components to see a possible parent ion, and the second MS analyzes the components that fragment from their initial parent ions. This gives us more information about the compound, and we're able to work backwards to determine the actual parent ions from the fragmentation patterns. And in this system, the options are you can either have just MS, which will send information over to the computer to have the mass to charge ratios prominent for the compounds and some waste, or you can have an MS hooked up to a UV-Vis detector, so you're able to get the UV-Vis absorption spectrum for the compounds as well as their molecular weights. Now, in order to get this different fragmentation for the MS, we use different ionization methods. So for HPLC, we typically use soft electrospray ionization method so that the compounds can be analyzed coming off of the HPLC first instead of being instantly fragmented. We can also use the atmospheric pressure chemical ionization or APCI method. Another ionization method is electron impact, but that's primarily reserved for GC because it fragments the parent ions before they've hit the MS, and that is not great for our purposes for what we want for the HPLC. Now, an overall of the MS instruments, they are very hard to maintain and they're very expensive. For an example, the turbomolecular pumps in our devices in TU cost $10,000 to replace. So the entire machine is very expensive because that pump is just one small part. But they are incredibly helpful and worth the hassle because they offer a lot when it comes to analyzing compounds effectively, efficiently. So that is the overview of my model, but take a second to appreciate my very shiny computer. All right, well, thank you for joining me and have a good day.